In this lesson, I look at cryptographic hashing. You can download the script for this video from above or at the end of the video. Before looking at how hashing works, let's review why it's important. We use hashing to ensure the integrity of information. When data has integrity, no unauthorized changes have been made in storage or in transit. We also use hashing to make stored passwords unreadable. Hashes can also be used to speed up lookups. Instead of searching for long strings of data, a search algorithm can use much shorter hash values. Let's look at how all of this works. To create a hash, plaintext is fed to a hashing algorithm. The hashing algorithm does not encrypt the message. Encryption allows reversal of the process. Hashing does not. That is not the purpose of hashing. The output of the hashing algorithm is a fixed length value based on the precise content of the plaintext. If one or more characters in the plaintext is changed, the entire hash value changes. There should be no entropy, no recognizable patterns shared by the plaintext and the hash. Further, the hash value is almost never the same size as the associated plaintext. Hash algorithms like SHA-256, the algorithm I used for this hashing example and all examples in this lesson, produce a fixed length value that has nothing to do with the length of the plaintext. Finally, hashing cannot be reversed. In other words, there should be no way to extract the plaintext from the hash. The hashing algorithm is unable to reverse its hashes. Not all hash algorithms are designed the same, but what we expect from a hash solution is the same across all approaches. First, the hash algorithm must be deterministic. In other words, if I run a message through a hash algorithm 10 times, the algorithm should produce exactly the same hash value every time. Hash computation must be fast enough that use of it in production does not affect system or data availability. It should not be practical. In fact, it should be highly improbable to extract from a hash value the plaintext used to create it. It should also be highly improbable that two different plaintext values might result in the same hash value. This is known as a collision. Any change, no matter how small, will cause a large change to the hash value. Further, the changes in the hash value should have no correlation to the changes in the plaintext. This graphic shows how changes in a message affect the hash value. Note the high entropy between the changes to the text and changes to the hash value. In the first change, I simply removed an apostrophe. Note the completely different hash. In the second change, the message is shorter. Note that the size of the hash value is fixed by the algorithm used. When using a hash value to ensure file integrity, the user runs the document through a hash algorithm. The hash value and the file are either stored together or separately. When the same person or another user opens the saved document, they run the document through the same hash algorithm. If the hash value matches the saved hash value, the document has not been changed. Message integrity and digital signing are related, and they help to validate message content and the identity of the sender. Alice runs the message through a hashing algorithm to create what's called a message digest. To create a digital signature and protect the message hash, Alex uses her private key to encrypt the message digest. The encrypted digest is the digital signature. The signature is added to the document, and the document is sent to Adam. Adam uses Alice's public key to decrypt the signature and access the message digest. Adam then recalculates the message digest and compares it to the value created by Alice. If Alice's decrypted hash value matches Adam's hash of the message, Adam knows Alice sent the message. Alice's public key successfully decrypted the hash, and it has not been altered after signing. Another use for hashes is protection of passwords. In this example, a user enters a new password for an application. The password is hashed with SHA-256 and stored on the application server. The password is never passed in plaintext over the network, even during authentication. Instead, authentication with a password includes comparing two hash values, the one for the password entered by the user and the one previously stored on the server. Microsoft takes more steps to protect passwords, as described at the link shown. Simple password hashes are not necessarily safe enough. If an attacker sniffs or otherwise captures one or more password hashes, she can run them through a password cracker. A password cracking solution hashes common character word configurations and compares them to the captured hashes. This is sped up by using rainbow tables. Rainbow tables are pre-hashed values. This eliminates the need to hash each value when conducting dictionary or brute force comparisons of password hash values. The values in the tables not only include letter combinations, they also contain words spelled with special characters, numbers, lowercase and uppercase, as well as simply appending numbers to the ends of words. One way to prevent simple hash comparisons is to add a salt value to the hashing process. Salting is a process of adding a set of random characters to a password before it's hashed. The random characters and the password are hashed as one plaintext string. The top example is our previous hash value with no salt. This hash would be easily cracked with hash comparisons. The bottom example shows adding a random salt to the end of the password. The resulting hash has no pattern relationships with the unsalted password hash. It would be impractical to crack this salted hash value with the hash comparisons attacks we've looked at. The salted hash and the salt value are stored in a secure account database. Well, that's it for this lesson. If you have questions, please ask. And until next time, be careful what you click.